My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 525. In this lecture, we will try to understand constraint optimization and PCA. So, till now, the optimization problems that we have seen are maximization of f of x over x or minimization of f of x over x. These are the types of the problems that we have seen with the logistic regression or linear regression. But if you recall our PCA, let's write the PCA formulation again. If you forgot, please go to the dimensionality reduction lecture and see that formulation of PCA. The formulation of PCA looks like this. Find the maximum u which maximizes, find the maximum u which maximizes 1 by n into sigma I equal to 1 to n u transpose xi whole square such that u transpose u equal to 1. This is the problem. Now this problem is similar to maximize over x f of x such that g of x equal to some constant. Yes, what is this sigma 1 by n into sigma I equal to 1 to n u transpose xi whole square is called objective function in optimization. This part, which part? U transpose u equal to 1. This u transpose u equal to 1 is called constraint, because you are saying that you want to maximize this 1 by n into sigma I equal to 1 to n u transpose xi whole square such that u transpose u equal to 1. If this constraint is not satisfied, if this constraint u transpose u equal to 1 is not satisfied, if you find some u that does not satisfy u transpose u equal to 1, you will not accept it. So the optimization problems where we have constraints like this, u transpose u equal to 1, is called constrained optimization problem. What is this? This problem is called constraint optimization problem. So the general constraint optimization problem. We will come back to PCA in a little while, but let's understand the general constraint optimization problem. It looks like maximum over x f of x such that maximum of f of x over x such that g of x equal to c and h of x is greater than or equal to d. Just see this one, maximization of x over x, this is called an objective function. What about this? This g of x equal to c, this g of x equal to c is called an equality constraint, because you have equal sign here. Then h of x less than or equal to d is called an inequality constraint. Suppose let's assume you have something like this, k of x less than or equal to e. When you have a constraint like this, like k of x less than or equal to e, you quickly change it by multiplying with negative sign on both sides. Then what happens? Minus k of x is greater than or equal to minus e. So given less than or equal to constraint, you can easily convert into greater than or equal to constraint by just multiplying both sides by minus 1. So that's why we are not putting less than or equal to constraint in the general form. You have equality constraint and inequality constraints of greater than or equal to symbol, isn't it? Now let's see how to solve this problem. We have seen how to find maxima and minima of f of x, but how to find maxima and minima given constraints g of x equal to c, h of x is greater than or equal to d. It is very important problem. Let's see. Maximization of f of x such that g of x equal to c, h of x greater than or equal to d. This is the problem that we have. We will modify this problem. We will modify using something called Lagrangian multipliers. The idea is as follows. Construct a new function called capital L. This function is called Lagrangian, and how does it work? I will say L of x comma lambda comma mu equal to f of x minus lambda into g of x minus c minus mu into d minus hx. Lambda and mu are called Lagrangian multipliers, and lambda is greater than or equal to 0 and mu is greater than or equal to 0. So given a problem like this, we converted this problem. Which problem? This entire problem. Given this problem, we converted given a problem of which type? Problem of this type is converted into Lagrangian. Now there is a beautiful piece of optimization. The proof of this is beyond the scope of this course. It says now we have to compute dou L by dou x equal 0, dou L by dou lambda equal 0, dou L by dou mu equal 0. If you solve all these three, let us assume we got a solution x tilde. What is this x tilde? X tilde is nothing but maximization of f of x over x such that g of x equals c and h of x greater than or equal to d. Let's revisit our PCA problem. What is our PCA? Find u that maximizes 1 by n into sigma I equal to 1 to n u transpose xi whole square such that u transpose u equal to 1. This problem can be represented by doing simple algebraic modification like this. How can I represent this problem? Maximization of u transpose s into u such that u transpose u equal to 1. What is this s here? S is covariance matrix x transpose x. What is my x? X is data matrix. Basically, what is this data matrix? It is a matrix of all of your x's. Let's focus on this particular which one we have to solve now. Instead of solving this, these are equivalent. This one and this one. These two are equivalent. Therefore, instead of solving this, now we will solve this. Why? Because solving this is very easy compared to this. Therefore, let me solve this particular problem. How can I solve? Just we will try to understand. Just see, this is the problem. What is my L? I am formulating Lagrangian. How can I formulate my Lagrangian? U transpose, just we already discussed how to formulate it. This one, U transpose SU minus lambda into U transpose U minus 1. Now what I have to do? Now the given, what is this S? S is covariance matrix. Now given this problem, let's write Lagrangian. What is my Lagrangian? I already discussed, isn't it? Now if I take derivative of Lagrangian with respect to u and set it to zeros, that is dou L by dou u equal to 0. What will you get here? You are differentiating partially with respect to u. Dou by dou u of u transpose su is su. Dou by dou u of lambda into u transpose u is lambda u. Dou by dou u of lambda, it's a constant, it will be 0. This differentiation is very easy. Just you can use, let's assume u is a vector. For example, let me take lambda u transpose u. If I say x1, x2, x3, u is a vector. What is u transpose u? U transpose u means column vector x1, x2, x3. What is u? U is x1, x2, x3. If I multiply, I will get x1 square, x2 square, x3 square. I have to differentiate component wise. Therefore, I will get, what will you get? I will get 2u. Anyway, it is equating to 0. Therefore, you will get simply. It is simple mathematics. Anybody can understand this partial differentiation. If you have any difficulty, please keep a comment so that I will explain. It is a simple thing. In similar manner, just this is a vector. This is a vector. Just this is covariance matrix, isn't it? Just if you multiply and differentiate component wise, it's a vector differentiation, is it not? You have to differentiate it component wise. So that what you are getting here, su minus lambda u equal to 0. The equation is u equal, what does it mean? What is this S? Where S is covariance matrix. What is my S? S is covariance matrix, isn't it? U is a vector, isn't it? This is the definition of what an eigenvalue and eigenvector are. What is an eigenvalue and eigenvector? Given matrix capital A, if AU equal to lambda u, something like AX equal to lambda x, people used to say. If AU equal to lambda u, then U is said to be an eigenvalue of A, and lambda is said to be eigenvector of A, and lambda is said to be eigenvalue of A. Is it corresponding to eigenvector U? Lambda is an eigenvalue corresponding to eigenvector U, isn't it? This is the definition of eigenvalue, and this is the definition of eigenvalue and eigenvector. This can be solved by saying U is the eigenvector of S, lambda is the eigenvalue of S. If you recall your PCA, when we learned PCA, we wrote the optimization problem and we said without proving that the solution to the optimization problem is to take the eigenvalues, to take the top eigenvalues and corresponding eigenvectors of the covariance matrix S. We did not prove, but here is the proof. This is what constraint optimization looks like. Just go through this lecture. If you have any difficulty, please keep a comment. In my next lecture, I will discuss about logistic regression revisited. Thank you very much.